SwayamPrabha. Digital India. Educated India.
In this lecture, we will start discussing about the most probable macrostate, and we will take the discussion ahead to look at Boltzmann distribution. We will discuss about maximization of the number of microstates for both bosons and fermions, and we will thereby reach the condition for the most probable macrostate, and then we will see that both of such distributions converge to a common one, which is called as the Boltzmann distribution at normal temperatures. Beyond that, we will introduce the partition function Q and then its role in expressing the thermodynamic variables in terms of the partition function Q. So, to begin with, we will like to obtain the most probable macrostate, and we recall some of the previous discussion that we had in the previous 2 lectures, and in those lectures we have discussed what a macrostate and microstate are, and in a given macrostate you can have a large number of microstates. We have constructed such diagrams and shown you how it can be done, and now we are going to move towards finding that most probable macrostate in which maximum number of microstates exist. Hence, we would need to find the specific distribution of the molecules across the different quantized energy levels, which we represent as Nj, so that the W is maximized. So, we will call that maximized condition of W as W max. We recall the function for bosons. You remember having looked at the derivation of this expression for number of microstates for bosons, and that was done by using rules of permutation, and we would like to maximize this function W now. In order to do that, it will be easier if you take a log of this function. If you take the log, it gives you this form in the form of a summation. So, originally in the W expression it was in the form of a product, now it becomes a sum of the logarithmic terms. And if you remember the energy diagrams, then you may recall that the transitional mode energies were very closely spaced one after the other, starting from the lowest energy level, which we called as the E0 dash, and with the subscript trans for the translational energy. So, these are very closely spaced, much closer than the other energy modes. If these closely spaced energy levels are bunched or grouped into a few degenerate states with essentially the same energy, since they are very close to each other, if you bunch them and bring them to an intermediate energy level where they can be put together as a group, then there will not be much of a difference in the actual energy level that they had and the one that they are assigned in the bunched or grouped form. If you do that, then there is a significant advantage. Each degenerate state is then going to get well populated, and the Nj values will also become reasonably large. Therefore, you can comfortably write that first of all the Nj's are going to be much larger than 1. The degenerate states will also be large in number. And how does it affect us? If you remember in the log W equation, there were several terms like this, which we left behind in the previous slide. So, now under the given assumption that both of them are going to be large enough compared to 1, you can approximate them in forms like this. Additionally, you can use this identity where you have logarithm of factorial x equal to x log x minus x. All the logarithms that we are talking about are of course natural logs to the base e. Once you bring in those simplifications, then the log w equation will simplify quite a bit. It will look like this. And again recall that we are talking about a population distribution. The moment we bring in the concept of macrostate, we are talking about a population distribution. So, starting from the lowest energy levels to the highest, you have a distribution of molecules, and which basically means that W is dependent on that population distribution. Therefore, log W is also a function of that population distribution, and if you want to maximize W, then if you take a differential of log W, that should be equal to 0. Again, by using chain rule, you can express the differential of log W in this form, where partial derivatives of log W are taken with respect to the different entities n naught, n 1, n 2, etc., and multiplied by d n with the given subscript, and then you sum them up and they should go to 0. So, with all these expressions and conditions that we discussed about, we should be able to finally show that d of log W comes to this form. Again, when we are talking about variation of Nj, that means there is some distribution change, some population distribution change, then this Nj cannot just change on its own. It is not going to be an entirely independent change, it is going to be driven by certain constraints. One very important constraint is that the total number of molecules available in the thermodynamic system cannot change, which means sigma Nj summed over all the levels gives you the capital N, which remains constant. And therefore, if you take a differential of Nj and sum it up over all the levels, that should also go to 0. And in terms of energy, you have epsilon j dash Nj summed over all levels, giving you a constant value. So, if there is a change in Nj, a differential change, then when you sum epsilon j dash dNj, that should give you 0 when summed over all the levels. Now, since you are imposing certain constraints and then you are trying to maximize a certain function, here in our case it is W, therefore, it is basically a problem of constraint maximization. And the most elegant way of solving such a problem is to introduce Lagrange multipliers. In this case, you need to incorporate 2 multipliers, because essentially you have 2 constraints to handle, and the constraint equations are now basically multiplied with the Lagrange multipliers introduced inside the sigmas. So, here is the first, here is the second Lagrange multiplier introduced into those constraint equations. The next step is you add the earlier derived expression for d of log W with the above 2 constraint equations with the alpha and beta introduced in those equations, and then you finally derive an equation which looks like this. So, this is the final form with the Lagrange multipliers introduced. That means, you now have set up the constraint maximization problem fully, and you can very well understand that if this sigma expression is going to go to 0, then for every level of j, every value of j that contributes in this summation, you need to have that expression going to 0 uniquely. Hence, for any quantized level, this expression is true, which gives you a form like this, and if you rearrange, then from there you get a population distribution N j expressed in terms of G j, the degeneracy level for that energy level, divided by e to the power of alpha plus beta epsilon j dash minus 1. At this point, we do not know what the values of alpha and beta are, but we are getting very close to obtaining that population distribution, which will give you the maximum number of microstates for a given macrostate. And this, of course, we have derived for bosons, because we started with the W expression for bosons. This particular population distribution will be represented with a star in the superscript, just to indicate that it corresponds to W max. So, it is not a general distribution, but a rather particular distribution where we are talking about maximized microstates, and corresponding to that, when we write down the N j, we write it with a N j star in the superscript, just to distinguish it. Now, if we substitute different values of j in the above equation, we will end up getting the population distribution in this manner, starting from the lowest energy levels. And therefore, you can understand that once you are given such an expression for the population distribution, you can get the exact number of molecules available at the different energy levels. However, we still have a problem here. We do not know what alpha and beta are. So, even though we would be able to get the other values in these expressions, alpha and beta need to be obtained. And once we obtain them, then definitely we should be able to get the actual values of the N j star for all the possible values of j. We will take up the alpha and beta problem soon, but before we move on, we would like to say that, like we did for bosons, we can repeat this approach for maximization of W for fermions as well, and you have to follow exactly very similar steps like the ones we followed for bosons, and then you should be hopefully able to get the population distribution of fermions, which gives you the most probable macrostate, and the most probable macrostate is connected with the maximum number of microstates, maximum number of microstates. So, they go hand in hand. This is something that you can try in your free time, try deriving this expression following exactly the same steps that we did for the bosons. Again, like in the case of bosons, since this N j distribution is a very particular distribution where you have attempted maximization of W, you should identify it separately from a general distribution, and therefore, associate a star with this N j. Now, if you recall that for fermions you see a +1 in the denominator of the expression, and for bosons it was a -1 in the denominator. That means, there is a difference in the denominator, it is just a term 1. We still do not know how big or how small it is with respect to these exponential terms, but if those exponential terms are rather big, then this 1 may not make much of a difference, but we again need to know when it makes a difference and when not. Now, if we are going to very low temperatures, how would the thermodynamic system behave at that time? How would this gas, how would the gas molecules behave at that time, close to 0 Kelvin? what will happen is that the molecules will definitely populate the ground energy levels under such circumstances. That is quite evident from our basic exposure of the different forms of energy that we talked about that a molecule possesses, and those energies are connected with the temperature, and therefore, if the temperature dramatically drops and goes very close to absolute 0, so does the energy, and therefore, most of the molecules are expected to populate the ground energy levels. Now, at higher temperatures, what happens is that the molecules get well distributed over a much larger number of energy levels. So, that is typically the behavior for high temperatures. High temperatures include temperatures that we see under normal conditions and mentioned as room temperature. Consequently, the energy states available at the different energy levels, which are of course defined through the degeneracy or statistical weights, are sparsely populated. So, this is true for the high temperatures. The consequence of such sparse population of states is that the Gj is going to become much larger than Nj, and that can happen if these expressions are much larger than 1, both for bosons as well as fermions, which would mean that the unity term in the denominator can be neglected at higher temperatures. Now, if you look back at what we saw in the previous slide, that they populate the ground energy levels, there what happens is that you may have this term +1 or -1 making a big difference or reasonably large difference, because you may not be able to fulfill this condition. And why won't you be able to fulfill this condition? It is because the degeneracy will come down significantly under such conditions with respect to the Nj, because most of the molecules are getting down into low energy levels and they are populating only a few of them, and therefore, the population becomes very large in each one of the states that they populate, and in such situation you may not be able to fulfill this condition. That is why at higher temperatures we are able to find that the unity term does not make much of a difference, while at low temperatures it does. So, at higher temperatures, since it removes the dependence of the distribution on the nature of the molecules, you would not be able to distinguish the statistics of bosons and fermions essentially. What does that lead to? It leads to a unique population distribution, which is given by the Boltzmann distribution, and this is valid for both bosons and fermions. The difference ceases to exist, and the Nj that you have over here would then be represented in a form like this, where we still do not know what the values of alpha and beta are, but nevertheless we assume that at some point we will be able to find them out, and once we are able to find them, we will be able to plug them in over here and get the distribution. And this distribution works for any kind of molecule, whether it is of the boson or the fermion kind. And again, because it caters to the W max condition, we would like to mention it as Nj star. Though we have not represented the Nj star expression in the bracketed or rather the boxed expressions here or before, but we have included it as a comment. So, when you use these expressions, do not forget to distinguish them in some manner. It is not essential that you always represent them by star, but you should have some demarcation for it. Boltzmann distribution will be used for all subsequent analysis that we will be doing, because the purview of our course is supersonic, hypersonic, hypervelocity problems, and usually we do not deal with temperatures very close to 0 Kelvin under such circumstances. Coming back to the expressions of alpha and beta, which we are yet to obtain, we will use this particular expression for beta without proof for now. We will be able to prove it a little later. In this expression, we find the Boltzmann constant in the denominator and the absolute temperature of the gas molecules. So, that gives you beta, and beta is often considered as a kind of a link between classical thermodynamics and statistical thermodynamics. If we substitute the beta value here, this is how Nj star looks, and when we sum the above expression over all the energy levels, obviously it should sum up to n, the total number of molecules available in the thermodynamic system. So, if you use this constraint, then you find a way to define alpha. So, e to the power of minus alpha is given by this expression. So, if you are interested to find a more direct expression for alpha, you need to take a logarithm of this expression, and then you should be able to do that. The other advantage is that now you can substitute this expression in Nj star. So, that is what we have done here. We have substituted it here, and therefore, we have got the Boltzmann distribution now available with us. If you substitute j equal to 0, j equal to 1 onwards, you are now going to get a complete distribution of the population across the different energy levels. So, this is a very important equation that we have here, the Boltzmann distribution with the alpha and beta already substituted into the equation. Now, we see that the energy that is represented in this equation, it is the total energy. The epsilon j dash terms, they represent total energy, and they can be segregated into two portions. One is the 0 point energy, and the other is the portion which is above the 0 point energy, which does not have a dash. So, if you are interested to express the Nj star in terms of the energy measured above the 0 point energy, which we are representing by Ej or epsilon j, then you can do a simple calculation yourself and see for yourself that the Nj star distribution can also be represented like the way we have done it at the bottom of the slide. So, epsilon j dashes are replaced with epsilon j alone, and you will find that the epsilon naught contributions in the numerator and the denominator should ideally no longer remain once you simplify, and therefore, this is how the expression is going to look like. We now introduce a function called as the partition function Q. It is also called as a state sum in some literature, and what is the partition function equal to? It is summation of Gj e to the power of minus epsilon j by kT, and you remember having seen it in the denominator here for the Nj star expression. Therefore, we are going to replace the Nj star equation that we had earlier with a form where the partition function is now introduced in the denominator. Remember that the partition function comprises of a summation over all the energy levels. Incidentally, Q is a function of temperature and volume of the thermodynamic system, and if we invoke the translational energy mode Q, which we have not discussed at length at this point of time, but we are still introducing it in a kind of ad hoc manner, we can show by using principles of quantum mechanics that the Q translational will come out to be of this form, where small m is mass of a molecule, k is of course the Boltzmann constant. We have an additional constant here, that is h happens to be the Planck's constant, and V happens to be the volume occupied by the thermodynamic system, which clearly shows that the translational partition function happens to be a function of both V and T. So, functionally you can write it like this. If you are now interested in expressing different thermodynamic properties, in terms of the partition function, we pick different thermodynamic property like say internal energy, enthalpy, entropy, pressure, some of the more important ones, and then we try to express them in terms of Q. What would be the process or what would be the approach that we follow? Let us see. So, we have the expression for the energy, the total energy. Here we have taken the energy above 0 point energy, but in the original expression we had epsilon j dashes, if you recall. You can very well do that here too, but then you have to introduce the epsilon naught values. So, when you introduce the n j star expression that you have got from the Boltzmann distribution, it takes up a form like this. Since Q is known to be a function of both temperature and volume, you can obtain del Q del T, and it does not really matter whether you write it for constant specific volume or volume, because the constant specific volume and volume are just related through the mass. And when you take the derivative, then the partial derivative, then basically the temperature dependency lies in the exponential term. When the derivative is taken, it will give you a form like this, and then if you combine all of it together, you will find that the capital E expression can be represented like this. That means, we found a way to represent the energy, the internal energy of the system in terms of the partition function. Now, when we have 1 mole of molecules, then of course, the N k, the product that you have over here, will be replaced by N A times k, where N A is the Avogadro's number, because that is going to be the number of molecules when you are considering 1 mole. Again, when you take a product of the Avogadro's number and the Boltzmann constant, what do we get? We get the universal gas constant, which is a constant for all possible gases, all possible species. Now, once you introduce this, you get the internal energy per mole, where the universal gas constant comes in, and you have the representation here. Again, if you go in the direction of the mass of individual molecules, then those values are represented by m, and then the mass of n number of molecules would then be given by capital M, which is the small m into the number of molecules. From this you can get the internal energy per unit mass, which is nothing but the specific internal energy, and that can be given by the capital E by m, the capital M being represented by the product of small m and capital N. Again, the ratio k by m gives you the specific gas constant. Therefore, through this you get an expression for the specific internal energy. From here again we can go into specific enthalpy, because we know about this identity that specific enthalpy can be represented in terms of specific internal energy and the product of pressure and specific volume, and thereby you also get an expression for specific enthalpy. Let us conclude saying that in this lecture we discussed about the most probable macro state through the maximization of the number of microstates, that is the W max. The most probable macrostates for bosons and fermions as well as the Boltzmann distribution were discussed, and we saw that at normal temperatures or generally higher temperatures compared to absolute 0, they both converge to a single distribution which is called as the Boltzmann distribution. We then defined the partition function, and we also started demonstrating how different thermodynamic variables can be expressed in terms of partition function. Thank you.